So the next unit that we're going to look at focuses on the electron and the effects of the differences in types of electrons on the atom and its chemical behavior. So let's start by talking specifically about, well, what is important about the electron? When we look at an element and its atoms, what we see is that the number of electrons and, as we'll learn in a bit, the type of electrons in the outer shell of an atom, that largely determines the chemical properties of the element. So since chemistry is a study of the behavior of matter, it's important for us to understand the concepts around the electron because those are largely going to be determinant in the outcomes that chemistry is seeking to understand. So the first thing we need to do is a bit of history and talk about where our ideas about the electron in particular have come from. And in the 1860s, two men named Bunsen and Kirchhoff determined that each element, when it was heated to a vapor or gas, produced a unique bright line spectrum. When I say a bright line spectrum, I mean an individual set of bands, like we see at the bottom for helium and neon, which are unique and distinct for every different element. Using this process of spectral analysis, where we analyze the light that's given off by specific elements, many different elements have been discovered which we didn't even know existed, such as helium. It's very difficult to think about, well, how do we even know it exists? Well, this is why. We know that it gives off a specific pattern of light, and that tells us that it is an individual element which is separate than the others. Now, the problem that Bunsen and Kirchhoff came up with is that neither of them could explain why they saw the patterns of light that they did. They didn't have a rainbow of light like you see produced by a prism in the diagram there, or the picture there. Instead, they had individual bands, and based on what was known at the time, they had no way of explaining why. So the first step in terms of explaining the bright line spectrum came from Ernest Rutherford, who did this very famous experiment which was based around shooting alpha particles, which are positively charged radioactive particles, at a sheet of gold foil. And what he observed was that every once in a while, although most of the time the alpha particles went straight through and hit this detector screen as one would expect on the other side, every once in a while there were large deflections that he theorized were because at the center of the atom there would be some dense, very small positive nucleus, and the remainder of the atom was actually largely made of empty space with electrons which would swarm around the nucleus, kind of akin to the motion of bees around a hive. Unfortunately, although his model was a huge advancement for us, it still wasn't able to explain why we got the bright lines that we did. Fortunately, though, Niels Bohr, who was a Danish scientist, did come up with a model which could explain the spectral lines for the element, and he called that his staircase model. Now, in 1913, Bohr stated that electrons around an atom could only exist in definite energy levels which possess a definite amount of energy. This is very much the same as you climbing the stairs. You're either on the first stair or on the second stair or on the third stair. You can't hover in between the stairs, and based on the height that you are up from the ground, you possess a specific amount of potential energy. Now, these energy levels that you would have talked about previous courses as being shells or orbits are found at very specific certain distances from the nucleus. And it's the distance that determines the energy at any given energy level. What he postulated is that the further the energy level is from the nucleus, the more potential energy that an electron in that energy level would have. So, like you on the stairs, the further you are up from the ground, the more energy you would possess. Now, he also stated that electrons can jump from one energy level to the next if they gain or lose just the right amount of energy. And they can gain that energy by absorbing high energy electromagnetic radiation. That could be UV radiation or microwaves, gamma rays, X-rays, from very high temperatures, because we know temperature really represents kinetic energy, or electrical energy. And that's what you're going to see in a lab that will do this unit. Now, this model that Bohr proposed in order to explain the bright lines for the spectrum of the elements actually worked very well because it defined how electrons could be given a means of producing light. Now, each line on that diagram happens to represent a different energy level with just the right and definite amount of energy. So how is it that the electrons actually get that energy and give it back off? Well, electrons ultimately want to possess as little energy as possible. So they try and stay in what's called a ground state, the lowest possible energy level. But if they gain a correct amount of energy, as we said, based on the temperature, electrical energy, or high energy electromagnetic radiation, the electrons can be caused to jump to a higher energy level, and we would call that an excited state. Now, in order to get back down to a lower state, because ultimately electrons want to possess as little energy as possible, they give that energy back off, and they do so in the form of light. The different colors of light happen to correspond with the different amounts of energy according to an equation that was set up by Planck, where E equals h nu, that's a curvy V, not an actual V, E representing the energy in joules, h representing Planck's constant, which happens to be 6.26 times 10 to the negative 34 joule seconds, and nu, which represents the frequency in hertz, which is a second to the negative 1. Since the frequency of blue light happens to be greater than that of red light, we could say that the blue light is higher in energy than red light. So the color of the lines in the bright line spectrum indicates how much energy the electrons have given off as they drop to a lower energy level. Blue light indicates that they have more energy to release than, for example, red or yellow or orange. That's what we know already from our perception of fire and the heat given off by fire. You know that the best place to roast a marshmallow is at the blue coals at the center, not in the yellow or red part. And the electrons are jumping from a higher energy level to a much lower energy level when they give that light off. Now, because electrons can jump to many different energy levels and drop back down to many more, the bright line spectrum for any given element usually consists of different colored lines. Well, why are those different bright lines different for every different element? Well, every element has a unique number of energy levels, and that's because it has different numbers of protons, which we know attract the electrons to the nucleus, and different numbers of electrons. We'll talk later in the unit that the effect that those electrons would have. Now, Bohr was able to use this model to very accurately predict the bright line spectrum for the hydrogen atom. But unfortunately, only for the hydrogen atom. It could not predict the bright line spectrum for any other element, and clearly this poses a bit of a problem for us. And this is where the ideas behind quantum mechanics come into play. That's where we'll start off next day.